Okay, so the first question, assignment, how many of you have done assignment? Okay, then let's try to do it now. This simple assignment, only few questions, very straightforward. Let's read it. A flyback converter in the figure has the following circuit parameters. Source voltage is given to you. Turns ratio N1 is to N2 is given to you. Magnetizing inductance is given to you. Resistance, load resistance, capacitance, frequency, output voltage, everything is given to you. Determine the required duty cycle. How will you find the duty cycle for this circuit? Formula for? The only problem is that first you should check whether it's CCM or not. So can you guys check if it's CCM? Can you guys check if it's CCM? कैसे पता? हाँ? क्या? Sorry? But still check na. Go ahead. Try to check if it's CCM or not. You just have to apply the same principle which we did for buck converter to this new circuit. How did we check CCM there? And then how do you extrapolate it and apply it to flyback circuit? So this is question 1 of assignment 3. Flyback. This is the critical condition here, right? So what you can do is first you can find out the duty cycle, assume it's continuous conduction mode, right? So that duty cycle, if you assume CCM, you can find the duty cycle by using the formula, right? By using this formula, once you have the duty cycle in continuous conduction mode, which is also true with critical conduction mode, you know that ILM will start from 0, go up to this point, come back, and that's how it would be, right? You can calculate the peak current. If you know the peak current, you know that in the diode current of the flyback circuit, which you can see, would be this one, right? With this peak value, if this is I1, this peak value is I1 into N1 by N2, right? Because of the turns ratio. So now if you know I1 from here, because you know the D, you can find out what is the peak value here. You know this I1, you can find the average component of this waveform, right? Then you can compare this average component with the load average current. If the load average current is more than this current, that means in reality this waveform is shifted upwards, right? This is also shifted upwards. That means it's in CCM. But if the load RMS current comes out to be lesser than this one, that means this is in DCM, right? In this case you can check. I'm also guessing that this would be in CCM, but you should do that. Any doubt? Do you want me to repeat any of this part? Of course, if it comes out to be DCM, then this D is no longer true, right? And then you have to write equation and do bit more work to find out. Okay, I'll just repeat what I said. You can determine the diode current assuming critical conduction mode. You know the peak value of the current because the previous peak multiplied by N1 by N2. You know the average current of this one. In the flyback circuit, the average diode current is going to be same as the average load current, right? You know the average diode current in critical conduction. You find the actual load current. What is the actual load current? The output voltage 5 volt divided by 5 ohm resistance 1 ampere. If 1 ampere is more than this average current, that means in reality this is shifted in y-axis. You are not operating in critical conduction mode. So that means you are in CCM. If it is less, then you are in DCM. Is that okay? Alright, I think if you do that and you can find the duty ratio, so A part is done. B part is the average, maximum and minimum values of the current in ILM. Once you solve the A part, anyways in the process you have found the average current, right? And now you can find out that this would be vertically shifted by how much value, so that the average current of this should match the average load current. So you know what is this vertical shift, and therefore you know what is the vertical shift here, right? So you can define the minimum value of ILM, you can define the maximum value of ILM. So yeah, in a way B part gets done automatically if you try to check for CCM, DCM. Is that okay? Right, because this waveform will be the same, only thing is it will be vertically shifted, and how much vertically shifted will depend on the load current, right? If load current is more, it will further go up, load current will further come down. Okay. Part C, the output voltage ripple. Again, we have not derived the output voltage ripple in flyback, we have derived it in, I think, buck converter. Probably boost also you guys derived as a part of the assignment. Can you do this one? You know the diode current, shifted version of this, right? Average you subtract, you would know the capacitor current. So if this is the diode current, you subtract the average value, you will get the capacitor current. Once you know the capacitor current, you can draw, just approximate VC. Current is negative, so VC is falling till this point. Current is positive, means VC is increasing till this point. Integrate from the minimum point to the maximum point. I equal to C du by dt. Use this equation. Integrate it from the minimum to the maximum point, and you will get your delta V. Is that okay? Is that fine? Anyone has any doubt here? No, if you have doubt, please ask. If you want me to repeat. No one? Average value of ID in flyback. Your question is, will it be same as average value of load current? Yeah, all the time it has to be same if your circuit is operating in steady state. During transient it will not be same, but if your circuit is in steady state, that means the average current absorbed by the capacitor is 0. So the average current of the diode must be equal to the average current in the load resistance, right? Because the average current in the capacitor is 0. Okay, can anyone answer? Now he is saying that in the flyback circuit, the diode current average is always equal to the load current average. Then what are we checking here? That's the question, right? Because this is diode current, uska average nikal ke we are trying to compare with the load current average, but he is saying they will be always equal. So what are we checking here? Anyone else want to answer his question? Full.
Average is always equal, but वो waveform भी होगा तो what we are doing here is उसका RMS value निकाल रहे हैं, इसका average value निकाल रहे हैं, and फिर we are comparing with V0 by 1 ampere. तो अगर ये 1 ampere से ज़्यादा आता है तो ये ऊपर है, इसका average ज़्यादा है तो इसका waveform उसके upward है.
No, average over full power cycle. Yeah. So average of ID will always be equal to average of load current. There is no question. We don't know the inductor current. So let's guess that it is operating in critical conduction mode. If it is in critical conduction mode, this is the average current of ID. Now is it equal to that? It should be, but it's not. That means my assumption is wrong. It is something above that. Okay, let me come back to this ripple part now. Ripple part, okay, so we find ID, we find IC, and then we find the minimum point, we find the maximum point, and we integrate from minimum to maximum. Why we integrate from minimum to maximum? Because that integral of I equal to C dV by dt, when you take dt on the other side, you will integrate dV. you want dV limits to be V min and V max so that you get the subtraction of the two, right? That's why you want to integrate from the minimum voltage to the maximum or maximum to the minimum. But the period of integration is between minimum and maximum. Now there's a little bit of difficulty, a little bit of a trick here. Trick means what may happen is that in this case, you see that the average current lies somewhere here. It is possible that you have a very small inductor and your current is something like this, okay, and in that case your average will cut the line at this point, and now when you subtract this you will get something like this. Is that okay? In that case the minimum voltage will appear here but the maximum will appear here, and again it will start reducing. Why? Because after this again the current has become negative. So whenever current is negative, your voltage will reduce. So your integration limits will change now in this case, right? So in buck converter that doesn't happen, but in boost it will happen, in flyback it will happen, in buck boost also this would happen. So you have to check the slope. You have to make sure the average is below the minimum this point or above this point, and accordingly you have to proceed. It's tricky. But why I said that is so that you have a larger ripple here, right? Yeah. Is that okay? VC at 0 plus is same as VC at capital T minus. Yeah, of course, we are damn sure about it. Steady state hai, capacitor hai. Yeah. They'll be slightly different. After all, it's a capacitor. So VC at 0 minus, depending on whether you have IC at 0 minus, if you have negative current or positive current, you can decide where will you have maximum, na? Yeah. Yeah. Voltage में ज़्यादा फर्क नहीं आएगा, but even there is some difference, but na where is the maximum? The maximum is at 0 or at because here it is falling again, na? This waveform. I'm not sure if I'm understanding the question. Maybe you think over it. You can ask it again after some pause. Anyone else has any question here? Okay, if no question, let's move to question number 2. And if you still have some doubt, we can discuss after class. Let's move to question number 2. That's the diagram. The question says that you have turned on the switch for some duration and then you have just turned it off forever, right? So it's not actually a DC to DC converter, not operating in repeated sort of fashion. You turned it on once, you just left it there and turned it off after that. The transformer winding had of course no current before you turned on, and at T equal to infinity again everything will die down. The self-inductance or the magnetizing inductance value is given as 1 millihenry. You have to find the total energy dissipated in the load resistance. What is the total energy dissipated in the load resistance? Energy conservation, so total energy dissipated would be nothing but the total energy that this guy stores at the peak value. Because after that only when this is on, this dot is at positive voltage, this is at positive voltage, so that means this diode is reverse biased, right, not conducting. So when this is on, the current will keep building up, then current will go to a peak value, then you turn off this, now this current will circulate in this way, leave the dot, current will start entering the dot, and this current will slowly reduce and all the energy gets transferred to the load resistance. So what is the total energy that goes from source to the load is the energy that is stored in this inductor at the peak value, right? You know the duration for switch turn on, you can find the peak value, half Li square is the energy, convert it into joules or millijoules or whatever is required, and that would be your answer. Is that okay? That's like some form of a flyback converter, not exactly operating as a flyback, but it's like one short mode. Any doubt? The next question, question number 3, very same question. The circuit is slightly changed. Question 3, instead of this diode here, you have put another diode like this. Now this works now in a little bit different way, because now when you turn on the switch, this dotted as positive, so this dotted also as positive, and this positive voltage gets applied across the resistor. Correct? Is that okay? When you turn off the switch, the current free flows like this, leaves the dot, current has to enter the dot, current flows through this diode. So in this case, the energy getting transferred to the resistance is when the switch is on and not when the switch is off, which was the case in the previous one. So now for the duration this is on, you know the voltage getting applied, you can find the energy flowing in the resistance, and that's it. You will get the total energy that flows in the resistance. Because when this is off, then no energy flows into the resistance. All energy gets circulated through this diode, and it just keeps circulating ideally through this channel, right? Is that okay? So when this switch is off, this current will circulate in this loop, leaving the dot, it will enter the dot and it will flow through this diode. It can flow through the resistance also, but why would it take a higher resistance? It can just flow through an ideal diode, right? So this current will continue to flow. In reality, it would die down eventually because of small resistances here and there, but then if it's ideal, it will probably continue to flow, but nothing will flow in the resistance. So as of now in question, everything is ideal, right? So the energy transferred is only when the switch is on. Question 4. Okay, now 4 has a complicated circuit which you can see here. All the parameters are given to you. It's a forward converter with a tertiary winding in it, and you need to find out, source voltage is given, load resistance is given, magnetizing inductance, the second inductance is given to you, capacitance, frequency, turns ratio and duty cycle, everything is given to you except the output voltage. So the first question is determine the output voltage, the maximum and the minimum currents in Lx, right? In forward converter, right, whether it operates in CCM or DCM, you check using this inductor, okay? Because as far as this inductor goes, you would always want it to become 0 before the start of the next cycle. Why? Because this energy you are not really using to transfer to the output. This energy you are drawing from the source and you are giving it back to the source. Because when the switch is on, it increases. When switch is off, this energy flows back through this tertiary winding to the source. This is the tertiary winding drawn in a little bit different way, right? So, not visible from there probably, right? But tertiary winding is made up of N3 and D, right? I have drawn it in a different way in the board earlier. This in picture it's in a different way. So ILM is not really helping you in transferring power from input to output, unlike a flyback converter. So ILM energy you would want to minimize. There is no point in unnecessarily draw and then send it back and keep doing it. So this guy you want to operate in DCM for sure. This is always in DCM. In this case also you should check this will be in DCM. But at a converter level, we don't define DCM, CCM based on this one. We define DCM, CCM based on the inductor which we are actually using to transfer energy. The same thing we have done with all the other converters also. So you check the Lx component here, and that will tell you first of all whether it's in CCM, DCM. If it's in CCM, you can just apply the duty cycle formula and get it. Is that okay? Any doubt? Okay. Then once you find the output voltage, you can find all the rest of the things. Just focus on this line, which is verify the magnetizing current is reset to 0 during each switching period. What it means is magnetizing current is ILM. Reset to 0 means it should come to 0 and touch 0 at least, or maybe remains at 0 also. That means in context to LM, it should be like a DCM kind of a waveform, right? So you need to verify it. You can check it when the switch is on, you can see how much it will rise, when switch is off, you can see how much it will fall, right? And that will tell you whether it will come back or not. Is that okay? Yeah, of course you have to go back and try. Since none of you have tried today, you will not be able to correlate, but it's simple. This question is very straightforward. This question is, you have been given the voltage waveform, you have to find the fundamental component of the RMS value, total RMS, total harmonic, all of those things, right? Just a small exercise, we apply this formula when it is problem. Okay, with that we take the assignment part, then we move on to the quiz. Any doubt in the assignment? We don't usually call it ECM. We just say that current will reset to 0 of the state. Yeah, we don't call it ECM. We say ILM current, always comes back to some other language. We just say circuit is ECM depending on the inductance we are using to transfer power from input to output. The significance is because anyways ILM is not helping transferring power from input to output, right? In zero, it's like you are giving energy, taking it back. Why do you want to unnecessarily process it? So you would want that ILM current to be as small, right? Question 1, you have any doubt? Figure shows below a DC to DC. Now this is actually called that, what is the circuit called? Everyone know this is called a buck boost. Non-inverting buck boost. The same as buck boost. Buck boost, you invert the output voltage is inverted, then it's not inverted. Why am I saying it's same as buck boost? Because you can turn off this S1 and S4, right? And that would only connect the inductor to the input side. That's it. When you turn on S2 and S3, the inductor will only connect to the output side. So with this combination, you can operate it just as a buck boost. Is that okay? And this circuit is called as non-inverting because the output voltage is of the same polarity, non-inverting buck boost. So if you know you only have to buck, I can say you can either operate it as a buck boost or you can just operate it as a buck converter by turning on S3. Part B is for case A if your frequency is this. So depending on your thing, right? Maybe some of you have operated in case 1, case A1 as a boost converter, you will get a different value. Somebody may have used it as buck boost, you will get a different value. Both are correct if you have shown it which way you have done, right? Is that okay? What was the values you got? Anyone remember now? For B part, 33.33. Okay, I messed up the values. Okay, what about buck boost? For buck boost? Okay. So you can see, right? I mean, even with the same L value, the inductor current ripple itself is more in buck boost. Definitely the output voltage ripple will be even more. Any doubt in question 1? No doubt. Okay, let's look at question number 2 then. For circuit shown in this picture, you know what is the name of this circuit? You know what is the name of this circuit? I also don't know. Some random circuit. So it's a circuit which again looks like a buck boost only. Only thing is at the output instead of the cap you have just a resistance now, right? But similar to buck boost because in switches on you are transferring energy from input source to the inductor. When switches off, that energy is getting transferred from inductor to the resistance. So some things are given to you: input voltage, frequency, resistance and duty cycle. Assume very large value of inductance, find the average inductor current. So how will you find the average inductor current here? Actually the inductor current would be something like this, right? Increasing with a straight line, falling with an RL kind of a circuit. Here we have said the inductance is very, very large. So that means practically nothing is increasing, nothing is going down. There is maybe just a slight increase and just a slight fall, right? This is how the inductor current is. Find the average inductor current. So the average voltage, since the circuit operates in steady state, the average voltage across inductor must be 0. That means the average voltage here, which you know, which is the duty cycle multiplied by the on supply voltage, must be negated by the average voltage here. Correct? So you know the average voltage that is getting applied to the inductor across this region, assuming current is almost constant, that average voltage should be equal to the voltage applied because of I into R. So you will get a value of current from there. Is that okay? Want me to repeat? Anyone? It's in steady state, so the average inductor voltage must be 0, right? So you know the average inductor voltage in this region. You can find the voltage applied in the inductor in this region. This is equals to I into R. So you equate the average, total average voltage equals to 0, you will get a value of I. There's very negligible ripple, so you can assume the I is almost constant for this part. Is that okay? That will give you the current in this duration, that will give you the average inductor current. To find the average resistance current, you again have to, use the duty cycle and find it. Okay, how many of you understood this? Raise your hand. Okay. You want me to explain it again? Which part? Follow, shuru se. Now go ahead. Where should I start from? This waveform is okay. This waveform is okay because inductor ripple is so small. Average value of inductor voltage must be equals to 0. That is also okay. In this region, the voltage applied is V in into D, right, into Ts upon Ts. V into D into Ts. This is the voltage applied here is V in into time is D into Ts. The voltage applied here is minus times this. If this is the current I into R into 1 minus D times Ts. Average is 0. This will give you a value of I, which is this current, right? Now this is the average inductor current. So the average resistance current is because resistance current only flows in this duration. So you have to find the average of this one, where this value is I. You have to find the average of this, and that would be the average resistance current, because resistance only conducts in this duration. The first duration resistance doesn't conduct. Okay. B part, if the value of L is reduced, what would be the impact on the average value of the resistance current? Okay, part B, if the value of inductance is reduced, that means now you will have more ripple in the inductor current, right? So it will go up, come down. The question is that what would be the impact on the average value of inductor current and the average value of the resistance current, right? In the on duration, the average voltage applied is still the same. So that means in the off duration, the average voltage applied should still be remain the same, because circuit is in steady state, right? This falling thing is exponential, right? So now if these 2 points are far apart instead of being same, and you want to keep the same average, right? In this waveform, if this is starting point, this is ending point, the average will be not at the midpoint. Right? If this would have been straight line, the average would have been at the midpoint. If this is decaying, then the average is lower than the straight line, right? So that means the average will be somewhere below. That means these 2 points are, this is how it would look like. So this would be closer to the average, this would be farther away from the average, right? Is that okay? But the average will remain the same. So answer to part A, the average value of the resistance current, average value of the resistance current, average value of the resistance current. How many of you think it will increase? Raise your hand. How many of you think it will remain same? Raise your hand. Oh my God. Average value of the inductor resistance current? Why will it increase? It will remain the same, right? No? Average value will remain the same, na? Because for on duration you need applied voltage into time is the same. So off duration is also the average of the applied voltage should be the same. And that is nothing but I into R. So if the average voltage has to be same, I into R has to be same, right? So average current, resistance is anyways a constant. So the average current has to be same, right? Isn't that? So the average value of the A part, the average value of the resistance current will remain the same. B part, the average value of the inductor current, will it remain the same? The average value of the inductor current? No. Because now this top point has gone up. So if you see the on this side, the average will become more, right? So the average value will go up little bit. Is that okay? Okay, second attempt. When you turn on the switch, okay, let me draw the circuit. When you turn on the switch, the energy gets transferred from this to this. When you turn off the switch, the energy gets transferred from this to this, right? Since I am closing the switch for the same duration, the energy that gets transferred from this to this is the same, and therefore the energy that gets transferred from this to this remains the same, right? I forgot the second story. Let me think. Let me recall. Just give me 1 minute. Yeah. That's the reason I stopped saying that. Okay, second version I'll have to think again. I'll answer you in the next class maybe. But from this one you can try to argue that the average resistance current will remain the same, but the average inductor current will grow up. Part C, L value is reduced such that the peak to peak value of the resistance current is 1 ampere. Find the value of L. What I actually wanted to do is to say this is 1 ampere, but I think peak to peak value of the current, because the resistance current is 0, the peak to peak value is actually this value, right? So that there was a little confusion in the C part. Some of you may have actually taken this as peak to peak as 1 and would have solved it. This is what I wanted to do, but then I understand that peak to peak actually means this. So some of you may have figured out that this is peak to peak, you may have not been able to find value. So we'll give you marks either way for part C, all of you will get the marks, right? I hope we have ensured it. If it's not ensured, you just give back your copies and they will do it again, no problem. Yeah. Can we write average resistance current is equals to 1 minus D times the average inductor current? Okay, that is not true, That is not true because this is not a straight line. If this would have been a straight line, this should be true. But this is not true because it's not a straight line. This is not a universal law, तो अब मान ले मैंने इंडक्टर करंट ऐसा बनाया, अब तो ट्रू नहीं होगा ये. So when is this true? When you have straight lines on both sides. Of course, if you have a DC, it's true. If you don't have DC, even if you have straight lines, it's still true. But if you don't have straight lines, you have exponential, this is not true. Okay, this B part, I will try to give you a better explanation in the next class again, don't worry. But C part, all of you are getting marks. Question number 3 is DCM question. You have to check if it's CCM, DCM, you have to solve it. I hope, how many of you actually checked it if it's CCM or DCM? 40% of you checked it, okay. Good. It was in DCM, right? Yeah. It was the last question. Must be. नहीं ये equation कहाँ से आया? We can discuss it after the class. 1 minute में equation लिखेंगे. Last question. I think this is something which we have wrote in class, right? Few points. So you just have to write those few points. Okay, so let's stop now. You can go and you can see your question papers if you want.